Alors, bon après-midi à tous. Good afternoon, everyone. Mon nom est Éric Dupuis. Je suis le directeur du développement de l'exploration spatiale à l'Agence spatiale canadienne. Je vous
I'm
remercie.
Eric Dupuis, Director of Space Exploration Development at the Canadian Space Agency. Thank you for joining us for this briefing on Canada's role in the James Webb Space Telescope mission.
Today by colleagues and experts, we have Sarah Gallagher, who's the Chief Science Advisor to the Canadian Space Agency President. We have Neil Rowlands, who is the FGS and nearest scientist at Honeywell Aerospace. We also have René Doyon, the principal investigator for the FGS nearest instrument, and Chris Willett, who is the Canadian Webb Project Scientist and Webb Archive Scientist at the Canadian Astronomy Data Center. Alors, on entame une période vraiment fascinante. Pour nous à l'Agence spatiale.
This is a truly fascinating time for us at the Canadian Space Agency, but also for the entire international space community. On December 18, the James Webb Space Telescope will be launched from Kourou in French Guyana. Exploring the universe is a very ambitious adventure, and we couldn't do it without the valuable collaboration of all our partners. And Webb is the result of over 25 years of planning and development with our international partners, be it NASA and the European Space Agency, and also our Canadian partners, of which the National Research Council of Canada, Honeywell Aerospace, formerly known as ComDev, the Université de Montréal, and the instrument team and the Canadian science team. Webb is the largest space science project Canada has been involved with since the inception of the Canadian space program 60 years ago. It's incredible to be able to say we are participating in a new stage in astronomy and in our understanding of the universe and our place in it. The Canadian Space Agency provided two important elements to the fine guidance sensor, and one of the four science instruments, the near-infrared imager and stealthless spectrographer, NIRISS. My colleagues will go into more detail about these contributions. The important thing to remember is that with this contribution, Canada will have observing time on the most powerful space telescope ever built. Our Canadian scientists will be among the first to study the data collected with Webb.
Canada is thrilled and proud to be on this journey. So, Sarah, why don't you please tell us about Canada's science objectives with Webb?
Thank you, Eric. It will be my pleasure. The Canadian astronomy community is fully engaged in the once-in-a-generation opportunity afforded by our participation in Webb and will play an active role in exciting scientific investigations. Some of the first studies will include one led by Canadian astronomer Dr. Els Peters from Western University. Her international team will observe the regions around very massive stars to help learn how these powerhouses affect their environments. And as we get closer to launch, we definitely feel the growing enthusiasm in the community in anticipation of Webb's groundbreaking science. Canadian Webb research programs will touch on a wide variety of major research topics in astronomy, including detailed examinations of exoplanets, which are the worlds around other stars, the search for the very first light sources in the universe, the formation and evolution of galaxies, the life cycles of stars, and closer looks at the small bodies such as icy moons and asteroids in our own solar system. Just to name a few specific projects, Dr. Maria Drought from the University of Toronto and her team will be exploring the cosmic explosions known as kilonovae. Olivia Lim and her team from the Université de Montréal will be studying the atmospheres of TRAPPIST-1 planets. And Dr. Matthew Taylor from the NRC's Hertzberg Institute will be looking at black holes. We are especially proud and pleased of the excellent scientific leadership that was shown by young Canadian astronomers who will be leading projects during the first cycle of observations. This interest from the next generation shows the vibrancy of our community. And really, it would be difficult to overstate just how revolutionary the Space Telescope is and what it means to researchers in Canada and around the world. Their work will help discover other worlds, learn more about the life cycles of stars, and paint a picture of the early universe and of galactic development and evolution. I'll let Neil describe how important the fine guidance sensor is to Webb's operations and how it underpins all of the telescope's observations. Over to you, Neil.
Okay, thanks, Sarah. Indeed, the FGS's function is to keep the observatory pointed at its targets with exquisite accuracy to enable the sharpest possible images during the data collection performed by all of Webb's science instruments. So I'll begin by describing the road to the creation of FGS and then a little more about how it works. From a technical perspective, the path of the Canadian contribution to the Webb telescope was not straightforward. Canada's contribution evolved significantly over the years. For example, in 1999, when Webb's 3 science instruments were selected, the guiding function was to be done by the NIRCam instrument. And 2 years later, it was realized that a separate guider would be required. So, in part due to previous Canadian work done providing a fine error sensor to Lyman Fuse mission, NASA's Lyman Fuse telescope, NASA agreed in 2001 that the Canadian contribution to Webb could be a fine guidance sensor and a science contribution to the NIRCam instrument. But in 2003, for a replan at the mission level, the science contribution, the Canadian science contribution, was moved into the fine guidance sensor, and this eventually became the instrument we have today, FGS NIRISS. The development of NIRISS, FGS NIRISS, took place over the years 2006 to 2012 and required many diverse and capable suppliers from Canada and the US. The flight model was delivered to NASA in July 2012 after extensive testing at David Florida Labs in Ottawa, and that's shown in the picture here. This testing required cooling the instrument to around minus 230 degrees Celsius. So it was not straightforward, but we accomplished it and got the instrument delivered. After delivery, the FGS NIRISS was also tested with our support at NASA Goddard, at NASA Johnson, and then at Northrop Grumman in California. So FGS is crucial to all the observations. In fact, FGS will be used in fine guiding mode for almost all of the science images to be taken by Webb. FGS allows Webb to latch precisely onto guide stars, and this locking on helps offset any movement in the telescope and capture clear and detailed images. The guider takes up about 25% of the total telescope field of view because of the need to always have a suitable guide star available in the view. So FGS has 2 independent imaging detectors that are fed by common optics. And using these large infrared detector arrays for the guiding function requires some sophisticated image processing, which takes place in the FGS flight software. So the fine guidance sensor is incredibly precise. It can detect tiny angular displacements of the telescope, equivalent to the thickness of a human hair, as seen from a kilometer away. Or, if you prefer, the equivalent of seeing somebody blinking in Toronto all the way from Montreal. So the FGS can sense these tiny movements by staring at one star and measuring its position, transferring that data to Webb's computers at 16 times a second. These measurements are then used to send commands to a small mirror inside the observatory that can be moved to correct for any vibration or drifts. So the FGS isn't just used for deep space observations, it'll also track guide stars as the telescope moves to observe objects within our solar system like planets, asteroids, and comets. So now I'd like to invite René Doyon to talk about NIRISS and the observations that we can expect.
Thank you, Neil, and good afternoon, everyone. I'm so excited to talk to you about the NIRISS, which is the Canadian-built instrument that will do, in fact, 3 things. We will study exoplanet atmospheres, study distant galaxies, and try to find very faint companions around very bright stars. So NIRISS is basically a spectroscopic instrument, and astronomers like to use images, of course, but one important information is actually spectroscopy. Et la façon dont on le fait, c'est que on disperse la lumière avec un petit prisme.
The way we do it is we disperse light, and allows us to see the distribution of light in different colors. And this gives us a lot of information, both on the chemical composition of objects, but also on their distance and their speed. So precious information and very important. So how do we do this? In this instrument, we have we can use different elements, and this is how we can change the different modes of observation. So we can see here a small orange prism. All the light of the telescope will be in this prism, roughly at 2 centimeters. With this prism, we can study the atmosphere exoplanets. So this is one of the points of our scientific team. We can study exoplanets that transit planets from our perspective, transit before their star. And doing this, the stars will kind of wink at us. We can measure the decrease in luminosity, but what is more difficult is to detect the thin layer of atmosphere around it. And that's one of the things that we will be able to do very specifically. So we propose to observe a large variety of exoplanets like Jupiter, which are, but who are close to their stars. We call these hot Jupiters, essentially. But also we will study TRAPPIST-1 system that Sarah mentioned, which includes 7 planets that circle a small star, 3 in the habitable region, 3 which may have life. So to answer this question is like, the first question to answer is, do they have atmosphere and what are they composed of? So the instrument will be able to do that. We'll be able to know if there's water, CO2, methane. So our observation program will require 200 hours. It's the most important observation program, which will be led by David Lafrenière from Université de Montréal. So now we'll add another dispersive element. This time we're going to the other point of the universe, far galaxies. One of the characteristics of NIRISS is it's able to capture a spectra of everything we see. Here we see certain galaxies that we will study, and we'll take a spectra of all these galaxies. So we can have a spectra of about 3,000 galaxies in one shot. So in one image. So we first of all wish to study these galaxies themselves, but we also know that the galaxy mode has dark matter, which acts as amplifies the signals of galaxies that are much further. That's why we hope to be able to find the first galaxies that appeared a couple of hundreds of millions of years after the Big Bang. So that's an extremely important scientific program. This is led by Chris Willett from the Research Center in Victoria. And the third mode, which is not the least, we will insert a small mask in the aperture, which will cover most of the light of the telescope, except for this segment. So this will allow us to study planets or matter that are forming close to their sun. So they all have a blind point at one point. We cannot see close to the star, but with this small mask, as it were, cover, for the first time, we will be able to see if there are exoplanets or planetary systems that are forming, and this will be an element that's absolutely unique to the instrument. So essentially, these were the programs for the Canadian team for this instrument, and I can say we just can't wait. Thank you very much.
That came in on social media from Corey on YouTube, and he's asking, when will the CSA and the Canadian partners start to observe using the telescope? Is there anything in particular you'll be trying to look at first? And I'll ask Sarah Gallagher if she can answer this question.
Thank you, Corey, for the question, because of course, as soon as this telescope launches, we want to get the data as soon as possible. But it's a very, very complicated piece of equipment, and it actually takes quite a while for it, first of all, to get to where it's going. It's 1.5 million kilometers away. And then also for it to unfold and to check out all of the instruments before we start getting the science data. So it takes about 6 months until we're going to start getting those beautiful data that are coming down. Canadians are involved in some of the very first science studies, and some of the first targets, they were chosen quite a while ago, are going to be looking at things like Jupiter, looking at galaxies in the very early universe, and also looking in the areas around massive stars where I'm looking at the molecules in those star forming regions. And there are Canadians who are involved in projects, those sorts of projects. So we're definitely going to be on the front ranks of getting in some of the earliest data. Thanks.
Thank you, Sarah. We have another question from YouTube, and the question is from Noah, who's asking, what does the infrastructure plan look like for possible servicing missions of the telescope? And I'll transfer that question to Eric Dupuis.
Thank you. So thanks for your question, Noah. You're probably motivated by the history of Hubble for asking that question. Hubble was serviced several times. There's a big difference between Hubble and James Webb, and that big difference, or one of the big differences, is where it actually lives. Whereas Hubble was in low Earth orbit, it was serviceable. James Webb will be at a Lagrange point very far from the Earth and in a location that is not readily serviceable. So at the moment, there are no plans to service Webb over its lifetime. So thanks for the question.
All right, thank you, Eric. That's all the questions we have from social media.
All right, thank you. So, donc, merci beaucoup à tous.
Thank you very much, everybody. To remain informed on the mission, I invite you to consult the Canadian Space Agency on social media, all the updates between now and the launch and after the launch. Thank you very much, everybody.